Hi everybody, Cal here with section 16.2, line integrals. Um, a lot to take in this section. You do want to spend a really goodly amount of time making sure that you're comfortable with what's going on over here, because the stuff in this section is really very, very important to the rest of the course, and if you don't understand section 16.2, you're going to have a lot of trouble going forward. Excuse me. So, on page 1087, your book introduces the idea of a line integral. And we start with the line integral of a scalar function f along a curve C. And the idea here is that you're just adding up the values of f along this curve C as you traverse the curve. The formula for it is down here in box 3. I wouldn't pay a heck of a lot of attention to the definition, because we're really not going to engage this on the level of a limit of Riemann sums. But for those of you who are interested in the theory, it is here. Our formula is down here in box 3. And the thing I want to point out here is that the formula for how to handle a line integral is really contained in the notation of the line integral itself. This is the integral over our curve C of f of x and y ds. Remember that ds tends to stand for arc length. And so what we really see in this formula is if we have a parameterization for our curve C, that's x is a function of time, y is a function of time, we sub that in for x and y, and we take the arc length along that little bit of curve. Square root of dx dt squared plus dy dt squared. And you can read that formula right off of the notation for your line integral. It's important to note that whatever parameterization you have for x and y must traverse your curve exactly once as t increases from a to b. Otherwise, you're double counting some points or whatever. So box 3 is really, really important. You want to spend some time there. And along those lines, glance at this blurb up here, but your meat here is example 1. You want to pay really close attention to example 1 and make sure that you'd be able to do something similar. I also really like figure 2 as a picture of what this line integral is. So that's pretty good. Example 2 goes into what to do if you have a piecewise smooth curve. If you have a curve like this where you've got different function or different parameterizations for your curve along different legs, like in figure 4. And example 2 shows you how to handle that. And so this is another really important example to work through. I would basically skip this bit in the middle of page 1089 about mass and center of mass. I mean, mass maybe. It's the same thing that we've been doing for mass all along. But for center of mass, I'd probably skip it. Which means also you can probably skip example 3. So then we define what we were just talking about was the line integral with respect to arc length. And now we're going to talk about line integrals with respect to x and y, which is a slightly different thing. Formulas are here, and again, I mean, this kind of just measures as it's all just in the notation for your integral, right? The integral over curve C of f of x and y dx is f of, where I've subbed in this parameterization, and my dx is x prime of t dt. This is a really standard differentials sort of argument. And similarly for y, but this dx is x prime of t dt. That's the idea. Everything is contained in your notation. And the blurb down here at the bottom is pretty important about notations for this sort of thing. Your book also talks about a common way to parameterize a line segment, which is going to be important because the hard part of setting up a line integral is parameterizing your curve. Example 4 is really good. I would pay attention to it. I would work through it. And the conclusion of example 4 is also pretty important, that the path along which you get from point A to point B is important when you're evaluating a line integral. It can really depend on the specific curve that you take to get from one place to another. Then we talk about line integrals in 3-space, and it's very, very similar. And Formula 9 is very similar to Formula 3, as you can imagine. And Formula 10 is very similar to the Formula 4 line integrals with respect to x and y earlier, whose number I'm forgetting. Example 5 and example 6 are good examples to work through. Finally, we get to line integrals of vector fields. What this largely measures is how much of a given vector field lies in the direction of the curve that you're traversing. And your book goes through the development of it, and again, you can kind of be a little blasé about this stuff, read it once and then move on with your life. This does cover how to find work as a line integral of force along a curve. And our line integral of a vector function f along a curve C is notated f dot dr. And again, the method to do this is encapsulated in the notation. If we have a parameterization for my curve r of t, I do f of r of t, I dot it with r prime of t. You can also think of this as f dot the unit tangent of your curve, but times the arc length. I don't love that approach. You want to think of this as the first thing over here. Example 7 is a really great example, as is example 8. These are both things that you want to work through. And the last blurb on page 1096 is also pretty important. I would pay attention to that. It gives you one last equivalency here. So that's what I've got for section 6.2.